Anyway, hey guys. So what I'm interested is negative transients. So if you look at this airborne system, and then we put this current aim to the ground, and if you measure this from this coincident loop, what you're measuring is sort of positive decays. So if you're measuring that, you should get the positive decay. So there's actually theoretical proof that you're not going to get any negatives just from this typical system. But interestingly, if you go out and measure the data at somewhere in Canada, you can actually measure this negative transient. So this blue guy at this northern platform, the northern area, it's a negative belt. It's a big blue, and there's another blue. And then if you flew with another system, you can see actually similar blues in the similar location. That means you can actually measure the negative values on the air. So there's now it's actually pretty well understood what it could happen is because of this complex conductivity or dispersive conductivity. It's basically like your conductivity is changing in time or frequency, so that's not constant, but it's dependent upon frequency or time. And if you have this effect and in the medium, so we call that as a polarizable or chargeable, then you can actually measure this negative value in the air. So now we pretty well understood about, oh, it could happen, and we can actually measure these values on the air. So then the next question is like, okay, we got this negative values, and somehow we want to extract some induced polarization information in the ground. And what actually happened interesting in this location, this is actually the kimberlite deposit. I'm not sure, Doug was actually briefly mentioning about this, but so if you look at the Ollie time, you can see the similar big blues and here, and then positive high values and this A4 location. And that means like this location, you may have some conductive material. So high values in the airborne system, that means you may have some conductive materials at this region. When you move on to a later time, this positive high anomaly or to negative anomaly, meaning you got these four different anomalies, four different chargeable anomalies at this location. So if you pick these 4 points and then plot that, and you can get this time decay curves. So like A1 to A3 is all negatives, and if you look at these decays, and A4 it's used to be positive, and that changes to negative. So there are different characteristics. So you can see that. Then the question is, okay, how do we interpret this and then extract some induced polarization information? So that I'm working for. I don't want to get into too much details, but like we sort of developed some workflow that we can handle this, recover conductivity and the induced polarization information such as chargeability. So at the end of the day, I get into the detail, we can recover 3D conductivity at this region. You can recover these two conductive pipes. You can also recover chargeability information. But that we got multiple time channels, meaning sometimes like that happens, it could have some different features. Remember that two figures have a different feature, meaning you can get multiple chargeability information. So, so this is at early time, this is at late time, so you can get some different 3D distribution, meaning now you're narrowing down different geological units for kimberlite. So it might be useful for this kimberlite exploration as well. So that's what I'm researching for. Thank you very much.
Thanks, Augie. Sorry, we'll get you afterwards.
Oh, you got 1 minute,
1 minute.
1 second left.
Yeah. Anything else you want to say?
Also, yeah, I'm more interested in this physics, and because like what's a little bit different for a typical ground IP, because you're usually looking for a very a slowly decaying IP effects, but here what you're seeing is very fast decaying. And one interesting thing is for permafrost. Maybe some of you guys might be interested. So permafrost is very chargeable, but like decays really fast. And like there are a number of case histories that you can see those effects in the time domain airborne system. So I think, yeah, that'll be pretty useful to estimate how thick is permafrost, what is the chargeable parameters, and that chargeable parameters is actually sensitive to the temperature of the permafrost. So that'll be my
Thanks, Augie.
Am I on time?
2 seconds.
Oh,
I don't know how to turn it off.
Perfect.
Perfect. Okay, so do you guys want to go just around the table? Does that work?
Sure. Paul?
Yeah, you guys can use your laptop or yeah.
Yeah, sure. Oh, yeah, you could also just
or you can
put your
it into
presentation
Slack.
into Slack. So just drag and drop should work.
Or any media,
Yeah.
USB, email.
Yeah, you just drop it right in. Your Gmail you should be receiving.
Okay. I'm in the US school, maybe.
Perfect. Are you okay if we keep you online?
Yeah, that's fine.
Okay. Perfect. And then just, that's fine.
Yep. It's a little late.
Okay, check your Gmail.
Alright. Yes. Okay.
Where's
All
your
right.
EOS?
Thank you. Well, this is put together in rather a bit of a hurry, so
Perfect.
I guess probably the salient point which I'd like to get across is that a lot of the work that we're doing is trying to push EM techniques into more complex environments, structurally complex areas with that are extremely resistive, with low signal and therefore low signal noise ratios. And a lot of the questions we're asking are sort of going along with that. So, okay, that's not what I just said, but so, yeah, so whether we're looking at cases where the primary driver is geologic mapping, or we're looking at hydrologic studies, we're moving into complex geologic environments, high degrees of faulting, often extremely large resistivity contrast, where you may be putting, say, high-rich sedimentary rocks adjacent to extremely resistive metamorphic rocks. This is just an example of a recent survey that was flown, actually a couple of surveys that were flown in the southwestern U.S. in Mojave. This is over the Fort Irwin National Training Center, and this is just a slice of resistivity. Sorry, there's no colors together, but reds and pinks are resistive. And you can see there's a lot of complexity in here, and the basins are compartmentalized. We have these really strong contrasts. And a lot of what we're starting to do is ask more quantitative questions out of this. Where exactly is the fault? Is the fault have a measurable, can we actually put a constraint on the dip? What is the internal structure of the fault look like? When we see units that are terminated abruptly, how well can we trust that geometry? And a lot of this is coming from, we're doing this in 1D still. We're using sort of your traditional 1D solvers, whether we're doing sort of deterministic inversions, with or without sort of lateral constraints, or in some cases we're using stochastic inversion. But we still sort of fundamentally come to these questions of how much can we say about these structures? So this is actually a ground example I worked on a few years ago. This is the Pinto Mountain Fault in California. And the question is this fault a hydrologic barrier between the north and south side? The idea is that the town of Joshua Tree wanted to put a artificial recharge facility on one side of that fault, and they didn't want all the water that they push in there to just go across the fault and out of the system. Because of various limitations in space, there's infrastructure, there's power lines, etc. Sometimes you have to work really close to the fault. So this is a series of time domain soundings in red that were on either side of that fault. And the question is, if we do a 1D interpretation, does that really mean anything? Or is the fact that there's fault geometry there and we're sort of violating the dimensionality of the system come to bite us? And this is just an example here where we took some synthetic models. So this is our fault right here with different conductivity structure on either side. We're showing a sort of vertical offset in structure here. And what this image is sort of the percent difference between the 1D response and a 3D response if you actually model it properly. And I've lost a color scale here, but this is basically sort of reds are where there's significant divergence between the two. So we kind of end up with a situation here. So I failed to mention this is in time domain. So this is 100 microseconds, 1 millisecond, 10 milliseconds. So up to maybe about 1 millisecond, you can kind of push within about 200 meters of the fault and get some valid information. But once you start to get closer in there, your assumptions start to break down. And so then you need to sort of be a little careful. But we continue to sort of forge ahead with sort of these 1D approaches with these airborne data sets where we can't go and model every single one of these. There's just not enough time today. And here's a cross section. This is also through that survey I showed in Mojave, where we have significant amounts of faulting. That faulting up against bedrock blocks. We have sort of alluvial basins. That we have upturned bedding. We have complex faulting and folding in here. But how much can we trust over this? And so that's kind of the crux is we're trying to push these models further in terms of quantitative information, looking at geometry of faults, and we run into these same situations in organic systems. We run into the same situations in sort of some of our geothermal examples. And I'll just leave you with this, which is, this is, I think, a nice example of sort of power up what we're doing here, where we can follow from line to line in an airborne survey and watch sort of this is actually fault propagation fold. You can directly really DM into map view, where you can see the faults sort of start to bend, or the genital folds get progressively bent up, and then you get fault breakthrough. But how much can we trust this if this whole sort of 1D assumption is still in the background of what we do? So I'll leave it at that.
Thanks.
Okay. Sure.
Takes time.
So Jaja, you just walked in, but you sat in the next seat for doing a lightning talk. Would you like to do a lightning talk? No, no pressure. But well, if you'd like to.
Do if you want.
Oh, I didn't prepare this. So what's the agenda?
That's okay. So what we're doing is just going around and giving a quick chat on like what you're doing in terms of research, what interesting questions you're exploring.
Oh, okay.
So
I
yeah.
don't have slides. I'll just give quickly.
That'd be great.
Why I'm interested in this course. So I'm my research focuses on joint inversion, data integration of seismic, EM, ground mag. Not so much on EM because I'm really new to EM. So into my research, I really want to understand the two parts: the computational parts and the physical parts. For the computational parts, enables you to get the inversion down, the computation down. But the physical part really matters because it allows me to understand why I'm doing joint inversion. Because there are certain types of studies that EM doesn't result to me combine these two. That requires a really good understanding of physics. So why I'm interested in this is because of all the images you guys generated that shows how the charges are built up spatially with time. That helps a lot. I wish I had that. We had such tools when I was in college. When I was in college, the professor just went out there and draw some wrote down the equations and suppose we understood everything, but no. So that the images you showed yesterday really helped. All the E fields, the B fields, DBDT field, and charges that helps me understand why we cannot use this target. So yeah, that right now I don't have a specific project on EM, but looking forward in the future, I really like to. So my research can be summarized as integrated study or integration of seismic EM, GravMag, ECI, everything. I'm interested in everything, so this really helps. So thank you.
Thank you. Thanks for letting us put you on the spot.
Yeah, I think I'm gonna go ahead and run the same project.
Sounds good.
I'm gonna stand up there because we have the same backgrounds.
Perfect.
The same project.
Oh, that sounds like a cop out to me.
As long as you jump in, you gotta.
Yeah. Do you want us to go separately? We could if you want to record
It doesn't matter.
Okay.
Totally doesn't
Let's do
matter.
it on this. Yeah.
It's family.
I'll let him do the background and I'll just describe what my aspect versus. Yeah.
Yeah. Okay. Can you?
Have your masterpiece.
Where's your-
That's why this PDF on there.
Think of how you
You guys want about that?
beautiful
Mike.
pictures. Each time you show up, you just
All right, let's try that.
beautiful pictures.
So that's Geo. This is GeoSci.
Oh, I haven't seen the pictures. Of the frogs.
Oh, yeah. Yeah. Okay, so hey everyone. Again, I'm John. I'm a master's student in the Center for Underground Construction and Tunneling. So our project is using GPR to look ahead of a tunnel boring machine. So a little bit about the project itself. There's a reservoir called Rondout Reservoir about 70 miles north of New York City that supplies the city with about half their drinking water. And the tunnel that delivers the water is currently broken, leaking water into the Hudson. And so the project is to tunnel around the broken portion and then cap it off. The local geology is mostly dolomite, limestone, and dolomitic limestone with some intermittent shale. There also have been some karsts found, but we're not really sure if we're going to encounter that. The typical fracture spacing is less than 5 feet. The objective of this is to provide a 3D depiction of the ground face, of the ground ahead of the face of the TBM or tunnel boring machine, to develop strategic approaches to treating and excavating adverse ground conditions. So this is going to be a supplement to measured while drilling data, so they'll do that, but we're focused on the adverse ground conditions include, like I said, fractures, faults, karsts, and fluid-filled voids. The big picture is for hopefully this method to be used in future projects, so hopefully we're successful and we can use it again. About the TBM itself, so it's 215 meters or roughly 700 feet below ground. 60 meters in front of the TBM will be probe holes drilled for grouting, but before they pump the grout in, we'll have about 3 hours to play with those probe holes to stick our GPR in there. There's about 12 meters spacing at the largest, at the end of the probe holes, so that these two are flared out a little bit. So 12 meters will be the max spacing. The first method is GPR, and we're playing with two different ideas: reflection, which is concerned with characterizing individual faults and fractures, the orientation, azimuth, stuff like that. But the drawback to this is, from what I understand, it's kind of arbitrary. The radiograms are in radial distance, and so they're a little more difficult to interpret. But it may be faster in the field than the next setup, which is tomography. So that's concerned with locating zones of high velocity or attenuation, which is, in my opinion, a little more pertinent to what we're trying to do, because we just want to find out if there is something or isn't something in front of the TBM, and not necessarily just characterizing any individual fractures or faults. But it's more logistically complicated because you have to deal with, receiver, transmitter in two different protocols at the same time. So the reason I'm here today, I wanted to get some input on anyone who's done this sort of thing on surveying time between the two different configurations, the inversion and processing intensity of the two different configurations, the thoughts on depth of penetration in carbonate environment, because I've seen
conflicting information. Some people said that carbonate environment is really bad for GPR, but then I've seen a lot more papers that say limestone is a perfect host for GPR because it's very resistant in general. And then any other resources on probe-hole geophysics, because there are a lot of papers on borehole geophysics, but not a lot of papers, actually no papers that I found on probe-hole geophysics, or GPR, excuse me. So I'm really interested in the logistics of getting the antennas downhole, especially 220 feet downhole, and moving them around. So, all right, I'm going to pass it off to him because he's got some cool illustrations.
I'll jump in, try to race through the background a bit. It's John.
Just wait.
Yeah.
Please.
Yeah, so again, my name is Brett Kravitz. I'm also a master's student. We're working on the same general project, just different aspects. I'll be looking at the annulus grouting. I'll explain what that means for anyone unfamiliar with tunnel boring machines. So again, John ran through this, but just to make the project seem a little cooler. It's a $700 million contract to drill this 2.5-mile tunnel by the state of New York. Yeah, as John said, it's leaking 20 million gallons per day in the Hudson's, and this is New York City's front, their water supply. So they're afraid, that this leak will just continue to intensify. It's been leaking like this, they think, for maybe the last 20 years. It's just been getting worse, and they're afraid this tunnel will collapse. So that's why they're doing this tunnel. So just a little background on tunnel boring machines, if anyone's familiar. So John's looking at ahead of the tunnel boring machine. What I'll be looking at is tunnel boring machines. They over-excavate, and while they're excavating, they're installing segmental liners continuously. And there'll be a small annulus gap between the rock and the segmental liners that are installed. So what they do is they simply drill holes through the liners and inject ground to fill in that void between the liner and the rock. And that route has some implications. Prevents excessive settlement, because the rock expands naturally, and structural stability of just the tunnel and the rock surrounding it. And it also provides additional waterproofing. So we're at the deepest point, 900 feet below the Hudson River. So you have very high groundwater flows and pressures. Those pressures would cause the tunnel built almost 100 years ago to start leaking out. So that grouting is important for that waterproofing. So my goal is to try to come up with a non-destructive technique to determine how that grout is forming. They're concerned about washout with these high groundwater pressures and flows, that the grout will simply just wash out after you inject it in there. They currently use destructive methods to determine how the grout forms. They just drill holes in the side of these segmental liners. It's expensive, time-consuming, and destructive to the line itself. So, using GPR, so the test line will look, just like this, just a straight line down the tunnel, and trying to look for voids, water-filled or air-filled voids that may be forming in that grout itself. So the research goals to determine a non-destructive testing technique. There's been some research on this before. It has actually been used before. It's just not in the standard. So we want to move this towards more of an industry standard, something that the client is confident in, that they can move away from these drilling holes in the side of their line. So the way to do this, first step is determine relative permittivity of the grout. The challenging part will be as the grout is setting and forming over time, the permittivity will be changing as the free water content is using. So we'll determine at what time will be best to run these tests at. So we'll be determining the permittivity here on campus, and then we're going to set up a mock panel like this, where we're going to actually put, insert some voids and do some tests to see, kind of make a basis of what we'll be looking for in the field. And then we'll be taking these testing techniques into the field. Here's some results from a paper that did this pretty much exact thing. have different materials. They were using soil, will be in rock. And ultimately transfer this testing methodology to the company constructing a tunnel for them to use going forward. We want to use GPR as it's more accessible. The equipment already exists. It's a little easier to run. Impact echo has been used, but it's a little harder to transfer that. I think GPR would be the ideal way to go forward.
Thank you, guys.
That's great.
Curiosity, is there a demo in the system between those panels or anything?
Yeah, there is. There's rebar. Yeah. So
I guess it's not spaced so finely. You're not totally close.
Yeah, I mean, from imaging that's been done, you could see, you know, you could see where the rebar is, basically. We're hoping that you can see that, okay. Essentially.
So, can I ask questions?
Absolutely.
With Lindsay's permission. So, like you want to see like give TBM this, and you're interested in like this part? Is that what you're interested in?
Yeah. So John's interested in the head of the TBM. So they route ahead of the tunnel boring machine as well to try to prevent water flowing in while they're cutting, and then they also route radially around it as they're going as well. So I'm more interested in the radial routing, and John's looking at it.
And you have a multiple transmitter of GPR or receiver.
Yeah, so we're thinking of, this is what I've seen done. I guess you could run lines radially, like circumferentially around the tunnel, but I've seen lines done just down the line. So you run multiple lines.
I assume the existing tunnel and its construction is very different than what's being done now.
Yeah, the original tunnel was constructed in about, I think it was 1930, and it was just cut and blasted.
So almost anything that's done now would probably be better.
Yes, definitely. The equipment and the tunnel boring machines that exist now did not exist when they just cut through. This is actually the longest continuous tunnel in the world.
Beat the Swiss?
Yeah, so the Swiss have the longest transportation tunnels, and that's what they advertise. Oh, we have the longest tunnel for cars or trains. This is the longest, just continuous. Pretty sure that's what I read. It's 80 miles long.
Wow.
They dug this in the 30s.
Really?
No, I'm sorry. Yes, this is a pure water. It's water. So they're excavating this tunnel for the next like 8 years around the existing tunnel, and then they're going to have to shut down the water supply, reconnect this new portion, and fill up some reservoirs so that New York City could eat some bagels.
It is, so you can click on the right.
So I'm Ben Bloss. Like I mentioned earlier, I'm one of Andrea's students. Was one of Andrea's students. So I look at, I do time domain electromagnetics, airborne, ground-based, and power lines have been my focus of my research. So this was a survey that we had flown in Iowa a couple years ago, and all the black lines are roads. You can see that there's a power line that pretty much follows all of the roads. This is an early time channel that we just gridded together, and yeah, you can see that there's some geologic regimes changing across the survey, but ultimately we see power lines everywhere. If we look at a late time channel though, we've lost pretty much all of our geologic response, and we only have a power line map. So it's a big problem in our world today. If we look at raw data, you just see all of these little stripes are power lines. And when you have a 1 by 1 mile gridded road structure or system in your survey area, you get power lines on a 1 by 1 mile grid also. So yeah, what we ended up doing was a 2-step culling process to get rid of these initially, where if the early times were affected, we removed the whole sounding, and if the late times were affected, we just removed the last half of the sounding. But you can see here that it's not so easy to just pick out power lines. There are power lines that have very little response in a power line monitor channel. And there's also a lot of near surface effects that come through in our data in the early times. So you can't just go through and say anything that looks like this is a power line. But if we look at a specific power line, we zoomed into it, we can see here that our contamination at late times is 800 meters to a kilometer in width around a power line. So we're losing a lot of data. If we invert this, and this is just modest culling, nothing too extreme, nothing too liberal, but you can see that we still have a lot of power lines coming through in our model section. And as we have these power line contaminations, it ends up raising our DBDT curves, which builds in false conductors in our subsurface. And if we use a lateral or spatial constraint on our inversion, we end up smearing these conductors into the model space. So here is just another power line, and I've gone through and I've extracted 5 soundings out of it. The blue and the cyan I'm calling clean soundings. The red and the magenta I'm calling dirty soundings. And then the center sounding here is the green one. And we can see down here that at the early times we see some effects in terms of amplitudes, but that's probably largely due to bird height elevation. As we look at the contaminated sounding, we can see that they're smoothly elevated. And that smoothly elevated part is the tricky part of this problem. Because if you look at one sounding, you can't see if there's contamination in it. You have to look at a profile of soundings to basically pick out your power line. Another interesting thing here is if we look at this green sounding, this is null coupled into our power line. And what that means is essentially we have a usable sounding at the very center of the power line. Interestingly though, if we look down here at late times, we see some of these oscillations, which generally have to do with capacitive coupling and IP effects. So this is probably just getting really close to a power line of whatever the material was, but a large metal structure. So what have I done about this? Basically, if you look at a power line, there's generally a neutral wire that runs along it. And those neutral wires are grounded at every pole. So you end up with this passive system that is basically a whole bunch of vertical loops of wire, or basically induction loops. And so as our transmitter is transmitting, this gets caught up into this circuit and just resonates. It's not a damped circuit, so it is damped, but we don't know how it's damped. It's damped naturally. So things are a little weird. When we go out to do an experiment, how do you do this? Well, you have to build yourself what we've dubbed a skywire. And you can see here that I have a wire running across the top, down each pole, and across the bottom. This is basically replacing the grounding structure, and we're just replacing it with a wire and a resistor. So what does the data look like from this? Well, I managed to put an oscilloscope across the resistor and the skywire to measure the decay of that. But this is the response from the TEM system, and this is a ground-based TEM system. And you can see here that we do see a jump here at 20 meters. But we only see a response at 20 meters. And if you remember back to that airborne example where we're looking at 400 to 500 meters on each side of a power line, this doesn't cover that. But we can see over here, if we just look at a sounding curve, all of them stacked up, that we do have this one spot that is smoothly elevated. So we're getting close. We're seeing similar structure, even though we're not actually fully modeling the system or even measuring a similar system. In terms of the skywire waveforms measured, these are completely unreferenced to the time domain system. So I had to go through and stack and manually do a whole bunch of stuff. And so I don't know where 0 time is in terms of the power or the time domain system. But I did go through and I identified peak amplitude in all of our waveforms. And so sometime the transmitter turnoff was sometime before that. But you can see here that we are largely decreasing in our values. But here at the 20-meter spot where we had that maximum coupling, we definitely have a jump in our amplitudes. We've also tried to model this in a couple different ways. So we wrote an in-house program that goes through and basically just models a vertical loop of wire. We use a horizontal transmitter, and we can basically measure the coupling effects from the transmitter to the skywire and back to the receiver. But these are only simple coupling mechanisms. It's just going from one system to another and back. We're completely neglecting the mutual inductance of the Earth here, between the Earth and the skywire. So if we, let me go one more. So we also used Enigma to model the system, because Enigma uses an integral equation approach, so you actually get some of those mutual coupling effects from the skywire. So here are 3 profiles of data. The raw data, the Enigma data, and the skywire mod data. This was the name of our in-house program. The take-home here is that if we look at the spatial extent, it doesn't quite capture what we're looking for. Down here, I took and I made a ratio of the secondary field, or the skywire response, over the background field, or the Earth response, trying to kind of figure out a metric for how do we measure the amount of contamination. And we can see here that when we drop the real data actually has some issues. What we're looking at here, because we're not going down to near 0, we're actually looking at the numerical precision of the airborne instrument itself. Additionally, I used a single sounding as a representative background for the entire profile, so that brought in some issues too. But if we actually look at how things decay, we've noticed that when we get to under about 10% contamination, we don't see any additional effects in terms of our raw data. So we've kind of developed this metric, but that's about where we've ended. It's a pretty tricky problem.
So, oh, most interesting. Yeah.
Anyway, that's what I have.
Cool.
Can I
Yeah.
one question? Because what you're expecting is pulse and mines, right? Like if you have this loop, or like a horizontal, vertical loop, and then if you fly over with the airborne system, in one part you're going to get like power line effect. Like because magnetic field looks like.
Right, but as you move your transmitter over and your receiver over, everything is symmetric on the other side.
Oh, so it's not just from it's not just from the power. So you're.
Are you talking about harmonics, like 60 hertz harmonics, or?
Yeah, something like that. That was what I was thinking.
So this is the red square wave here is our transmitted signal. You can see here that it's a 30 hertz signal. I've overprinted a 60 hertz power line signal, and this would be our decay, our DVDT, from the power or the transmitted signal. And if we just extract our off times, we can see here that our 60 hertz and our DVDT the 60 hertz is getting sampled at the same point in every waveform. But our DVDT is flipping polarity. So if we flip every other one of these and sum them,
Right.
we end up with this is our measured response. And once we sum all of those, we end up back with just our decay.
So like with the stacking procedure, it's gone.
Yeah.
So what you're seeing is actually you're exciting that loop from your
Yeah.
wire, and then
Have you found that 60 hertz is actually pretty stable, or do you get drift around 60 hertz?
So Paul's been working a lot with GIC stuff, and I've been kind of tagging into some of his meetings. And the 60 hertz is very stable.
Okay.
There might be some fluctuations, but in general, they really try to keep that stable. The load on the line can cause a little bit, but it recovers pretty quick. From everything we've heard from electrical engineers.
Yeah, I mean, the stability of the 60 hertz is a function like the big transmission lines, those are really quite stable. When you start getting down to distribution lines, down to like, you know, that line which is feeding Farmer Joe's, you know, well pump, that starts to get kind of lousier. It's also lousier usually in other countries where maybe the loads aren't balanced as well. But even so, we're pretty convinced that the effect of 60 hertz is pretty minor.
Yeah, or 50, or wherever you might
At
be.
least compared
Okay,
to the
yeah.
sort of this inductive component.
Yeah.
And I think, you know, I don't know sort of what level of 60 hertz you would need in order to really see it. I guess we haven't really done tests where we've had the repetition frequency such that it doesn't cancel out.
That would actually be interesting about now that you mentioned that, because you could take the proton, you could actually switch
You could flip to 50
50
hertz easy, yeah.
Yeah, and just see how bad it gets.
Or we could take the walk time and rewrite a script.
Yeah.
There's a lot of things we could do. It's just,
Now that you know.
yeah, I'm done.
Well, the other thing you could do is, right, there's 50 and 60, where you just, I mean, you could see exactly how bad it would be if you set your base frequency such that instead of canceling it, it actually was constructively such that you would stack it. I guess that would be one way.
With the walk time, you can do that because it's totally
You can do it,
programmed.
yeah, they're specified.
With the proton, it's really 50 or 60 or
Yeah.
some
Well, and that changes on the proton. It changes all of the set frequencies on the inside, because you know there's what each receiver transmitter pair has 3 frequencies. So
and they're all some multiple.
except for that's a whole nother story. Actually, we won't get into that. But yeah, they're all harmonics or subharmonics of 60 hertz or 50 elsewhere. So.
Do they monitor in this grounding loop how much current is actually going into the ground?
You mean within the power system?
Yeah.
No.
There are GIC monitors. They are few and far between. Those are not at, like what Ben's talking about with sort of like, you know, grounding at every power pole.
Right.
They aren't monitoring it there, but for the GIC problem, this is, I don't know if anybody spelled out geomagnetically induced currents. This is the concern about induced currents getting into the power system and causing problems with transformers or collapse of the actual voltage collapse. There are GIC monitors, but they're usually at the ends of the sort of transmission lines, or where transmission lines go into distribution lines. So the power network, as we understand it, is there are substations usually every 50 to 100 kilometers, and where they put monitors is on the neutral line of the transformers. And so yeah, there are a few measurements of sort of the GICs, but not at sort of
Not at the scale.
Not the scale you need.
Not the power poles. I also,
Just on this topic, I guess that you've been in touch with Jeff Love, but I think he's said it's too bad.
Oh.
Because he would, like, that's what he's doing.
Yeah.
Exclusively. And I think he was going to come.
He was
I mean, I
trying
could
to
happily
come.
yammer about that too. You know, but yeah. So.
Hi, I'm Brian James. I have nothing to present up there. I learned about this about 6:30 this morning. To come on today. So, as I mentioned, I've been in a different industry for most of the last 20 years. But let me talk briefly about what I was doing prior to that, from mid-80s to mid-90s roughly. I was working on concepts to imaging of the subsurface using transient electromagnetics that was based upon determining where the currents are flowing in the earth, how that is mirroring geologic structures. This was all instigated by ideas of, some of you might be familiar with these, ideas of source-oriented modeling versus field-oriented modeling. And that was from the context of gravity and magnetics. You know, I had the benefit of listening to people like Tom LaFair back in the day, lecture on things like this. So it got me thinking about how to do the same thing in electromagnetics, where the sources now are currents, but we obviously have a harder problem because it's all changing with time, as opposed to the electromagnetics case. I developed methodologies basically to do imaging of the subsurface based on this connection of identifying from measurement of magnetic field data and fence profiles to turning that into a picture of where the currents are flowing in the subsurface and relating that to geoelectric structure. So that's what I was doing about 20 to 30 years ago. And back in the game just now recently, and I'm interested in similar problems, and it sounds like everybody is solving geologically complicated problems. And transient electromagnetics is a really strong technique, but it's really hard. There's a lot you have to get a handle on. And certainly I think everybody understands the limits of 1D approaches to analyzing that kind of data. If you just look at the picture of where the currents are flowing in the earth in a transient system, you have essentially no coupling at all to what's directly beneath it. It's going down and outward, as we all know. So the idea that an anomaly appearing in our transient electromagnetic data at some later point in time, as that being something at depth beneath you, is kind of specious, I guess. We all understand that's not the case, but we have to have a way to really fully take on the geologic and geoelectric complexity and understand where the source of these anomalies are coming from. So those are my interest areas, and I have concepts that I'm starting to pursue again that kind of take off with what I just described, where some stuff I was working on 20, 30 years ago. So we'll see where it leads.
So are you primarily interested in methodologies, or do you have a specific area and problem that you're
No, I'm not. I'm interested in methodologies. You figure out through the years what you're good at. And my skills are in methodologies, understanding the physics, developing algorithms. That's what I did in the defense world for years. No, but the geophysics helped me solve a really challenging problem in that world, because it's interesting, the techniques that come up in the geophysics world, and you go to some other realm and you introduce that idea and they look at you like you're an alien, because they've got no concept of these things, and yet the geophysics background helps you to really tackle a lot of complex problems. I dealt with things like HF, radio propagation, characterization of the ionosphere. That's a geophysics problem now with a time variable. I also have done a lot with RF geolocation. That's a problem that world deals with a lot. And I actually introduced some geophysics ideas and how to solve one of those problems correctly, where they had been going about it incorrectly, using some techniques that they didn't even realize they were violating physics. They actually were forming solutions that violated causality. They didn't realize it. But with a geophysics background, you go, wait a minute, you can't do that. And you have to do this instead. So the geophysics methodologies and concepts and training and background can be really valuable, not just in the world of geophysics and geology, but in other realms as well.
I've got something on.
Perfect.
So I'm involved in a lot of different types of EM problems these days, and some of them are things that my students do, like Ben talked about pretty much his problems.
I don't
Roxana. Oh, is it not?
I don't.
I just dragged and dropped it in. I don't know.
Can you?
Yeah. Is it in the random channel?
Yeah,
I see random.
Oh, I closed it a lot. See, he has a
No, it's not on random.
Yeah. It's,
Yeah.
You did buy me that one. So.
Technically, it says. Come.
I think I just dumped it into the first page. But anyways. Actually, this doesn't work all good.
So I just X out of the banner. I was just shutting this down. It was a no. There was a, they just had a banner alert up top, so I just got rid of that.
Did you say we're supposed to be on random? Or?
No, you can do that.
On your computer?
That's if you wanted to. So you can X out of that.
Did we find it yet?
No, I don't see it in here, so it may not have gotten uploaded.
So I'm involved in a number of different projects, and what I'll do is I'll present one up here, something specific, because I'd kind of rather somebody like Ben talk about what he does, or when Roxana comes later, she'll talk about what she does. Also got other graduate students working on projects like casing as well, from different numerical approaches, students working on projects like GIC, so this whole storm time induction hazard thing, kind of the MT problem in reverse, if you will. I start this off with acknowledgements because I know I just threw a bunch of slides on, so I just wanted to make sure that with this particular project, I made this clear that this is a huge collaborative work that I got involved in during my postdoc, and it's a problem that I think about quite a bit and work on quite a bit still. So I did a postdoc in GMR, and that was 5 years ago now, which is the German Marine Research Institute. Marion Yegan was my supervisor at the time. Sebastian Holtz is a research scientist there. And there were a lot of people who got involved in this, like Fugro, and there was RWD, there was University of Toronto, and all sorts of bits. I got there and they had built this system, which is pretty unique. I'd been doing marine EM for quite a while, and normally you do marine EM where you tow transmitters or you tow cables, and they were dealing with very small scale near surface marine problems. So things like marine mining application, they were dealing with mud volcano imaging, situations where basically you couldn't do your standard tow a cable on the seafloor or drop nodes and tow transmitters because you just don't really have the spatial resolution. So they basically had constructed this right before I arrived. And basically it's conceptually similar to the way you do marine EM, except that you drop electric and magnetic field receivers on the seafloor, and then you actually go and you pogo around either with an ROV or with a frame of some mechanical device, and you actually like touch down and make transmissions in various locations on the seafloor. So I mean, this is kind of what it looks like, and this is, if you know anything about marine EM, this is very standard. The receiver side. It also looks like a small MT station, I guess, too. But the transmission is what made this very unique, because we don't now have tow lines. We kind of have much more control of where the transmitter goes. And they had just done this when I arrived, and this is like 2010 when this was done. This is a mud volcano. This is offshore Egypt, and the question was, okay, this mud volcano is being produced most likely due to some sort of hydrocarbon trap that's been broken, perhaps partially. And you've got all this bubbling, and it's an active mud volcano, so it's just there's fluid flow coming up. Can we image what's happening in the really near surface to understand if it's
gas filled or if it's water filled. And the one thing that I want to just point out here is that this is really awkward and strange geometry, acquisition geometry. All the X's are transmitter locations, and all the white squares are receiver locations. They basically just took this ROV and they just touched it down in X-like patterns. So they actually had all these different polarizations where they transmitted on the seafloor. And so you end up with this geometric mess. Like it's just, the data was just sitting there and nobody knew what to do with it. I mean, the idea was we just got to go out and fully 3D invert it because we just can't do any stitched 1D anything because it's just crazy to do anything other than that. But you gotta somehow look at the data before you start to jump into things like full out 3D inversion. And so we sat there and thought. And then I got there, and so my contribution was to try to figure out what to do with this, which wasn't actually why I was brought on as a postdoc, but I just ended up getting into it. We realized that you could take a determinant, kind of like a rotational invariant of this thing, because you have basically two transmitter orientations and two receiver orientations. And if you take that determinant, you do it for all times, because this is a transient system. So you basically switch off or switch on, and you measure sort of decay afterwards in the electric field. And so now you get a situation where you have removed the degree of the problem with rotation. So it's kind of like we kind of compressed all our data into something a little bit simpler, and it lost some information, but now we can interpret it a little bit better. So then you take the next step and you say, all right, I'll look at this time domain EM data, and I want to glean the most useful data out of it. I want to just look at an arrival time. So I'm gonna come up with some apparent resistivity from this data, which is related to the peak electric field that's measured. And what I'll show you what I mean by that in a sec. This was a real eye-opener. I've shown this a few times in a few different places, and I still really, really like to show this because the mess in 2010 was just, you couldn't even look at the data. But what I've done here, every transmitter receiver location that we've got in the mud volcano, the data looks different. But if you take every pair and you turn it into a rotational invariant, and then you just normalize by a maximum amplitude, and then you normalize by some dimensions time, you can dump all the data on top of it, split each other. And so we didn't even know the data was just bad. We had no clue for like a year or two until we were able to do this and look at it. And what you do is you take it and you differentiate it, because what you do is you get the, oh man, you get the impulse response. I'll show you one thing.
Keep going, yeah.
You take the impulse response. So you can actually bin it in what looks a whole lot like a seismic CMP gather, right? Larger offsets correspond to looking deeper, and smaller offsets correspond to looking shallower. And you take that arrival time, right? And you say, well, if that peak is earlier or later, right? Then that'll correspond to higher or lower resistivity, and then you just map that out basically. And so after that, we were able to do this, which actually let us say, okay, something's going on here. It's actually worth taking the next steps towards 3D inversions, which actually haven't still been done. I mean, this is something that still is outstanding. But you can come up with an apparent resistivity map on this thing, and you can say, okay, well, in the center of the volcano it appears to be more resistive, and on the outside it looks to be more conductive. And you can just break it up into different depth slices, basically, in a way, and you can sort of say, hey, at the larger depths, we're seeing a more resistive zone. And I'll just fly through this really quick, if that's okay.
Yeah, go for it.
Yeah. So then I was already there, and then they just this is, I keep saying that this institute is a lot like, you know, Indiana Jones at the end of the Raiders of the Lost Ark, where like they put the Ark away in this enormous archive. If anybody remembers that part, it's very end, because GMR is fantastic at getting data, but there's just it's almost like they just get too much of it, and so they just kept going to sea and kept going to sea and kept going to sea, and there's just more and more data. So this is offshore Norway, and these are gas hydrates and all this high resolution seismic data, and they were looking at a chimney. They decided, let's build a new type of transmitter. So this is now not an RV.
Need more data.
Very expensive to actually rent, and you have to have the right kind of umbilical connections on a ship. So this is something called Sputnik, which Sebastian built. All four of those electrodes are transmitter electrodes, and it's a mechanical thing where when it touches the ground, it opens up like four basically, and it's just really cool. It's kind of super impressive. If anybody ever meets Sebastian, you'll know exactly what he just likes to do stuff like this, so it's cool. There was a survey map that they did, more gridded in this way. Now there's red squares being receivers and yellow squares being transmitter locations. You can go through and look at the data in the same way, right? Because again, without wanting to 3D invert it, you just want to look at what's going on. So here's kind of like these receiver gathers now, right? But they've been turned into these rotational invariants. We've taken this impulse response out of them, and now we're picking arrival times. And so you can actually just look at the data immediately and say, hey, RX2 sees significant variation in arrival time, because all the offset information has been normalized out. And so everything you see is to do with some sort of structure, potentially related. So you can see it immediately in the data once you start to kind of spin it in that angle. And I won't dwell on this too much, but they had OBS stations they had dropped, and they'd shot into them from the ship. So the top is actually an apparent resistivity sort of pseudo section map that was created, kind of like what I showed with the mud volcano, but then in slices in the bottom is an OBS velocity map. So again, this is these projects. I'm not there anymore. It's been years now, and I talk to them. I work with them a lot still, but I feel like these projects are just done. We do a little something, and then there's more data, and then more data and more data. And so I keep thinking, hey, we should visit this one, for example. We could actually 3D invert this. And then we forget about there's the mud volcano stuff too that nobody's 3D inverted either. Like it's just this stuff just keeps coming. Offshore Taiwan, I was just coming to CSM, I think at that time. They were looking more at gas hydrates, and they had really high resolution seismic data. They did, I guess this is their cruise path, and were able to kind of identify various targets. In this case, they were actually, I didn't go on the ship, they were dropping OBM receivers in a line, and then they were putting Sputnik down and transmitting along that line, and that's on the crest of a ridge. And then they cut another ridge. And then we were trying to look at this, and this is something that some of the arguably probably shouldn't have done, because it's deceiving. It makes it look like it's a 3D inversion. We took a depth converted seismic image, which is what you see behind. Then we took basically imaged apparent resistivities and kind of converted them to a pseudo depth, right? So you could say, well, we've got twice the offset, half the offset. That's approximate depth of investigation, and let's just overlay those things. And GMAR, being a very geological place, wants to see that kind of stuff, right? And it's not a proper comparison. I mean, the depth is not depth, but we were saying, hey, we're seeing resistivity anomalies in certain zones where there are definitely seismic anomalies. So again, this data needs work, right? I mean, because this is definitely not the end of the story for any of these data sets, and there's more. I mean, I've shown 3 examples, and there's probably at least 5 more examples of really high quality data sets. And when Roxana comes later today, she'll talk about doing time domain EM with loop sources on the seafloor, because that's like the newest thing that this group is trying to do, and we're still working on that. So yeah, lots of data, lots of stuff to do with it, and really unique data. And what appears in all 3 examples, there's something in the data. Like, it's not just junk, right? Because it could be, you never know. But it appears that there's something worthwhile going forward with all of these examples. So that's it for me.
Are you able to actually know what the orientations of the transmitters and receivers are?
Yes.
So
you could rotate it, and
no, but if you're going to invert it,
yes,
forget about going to invariance, but just actually say, okay, I know this transmitter is in this direction, receivers in this, so you know that.
Exactly. Yeah. And even before we came up with this invariant idea, I remember just being on the blackboard and trying to figure out how to rotate all this stuff, and just realizing, like, this is so much work to do something where we don't even know if there's anything in the data yet. So the possibility is definitely there, because there's compasses and heading and tilts even on the instruments. So we know basically dip and azimuth and all that of each receiver and each transmitter position as well. So all the data is there.
Yeah. So you've got electric field transmitter, electric field receivers, right? So you could use reciprocity?
Yes.
So then you've only got effectively like a half a dozen sources. How many receivers did you have? Not very many.
It depends on which survey, but maybe on average about 8 to 10.
Yeah, and you've got tons of transmitter locations,
exactly.
right? But you could use reciprocity, and then
Yeah, and then use
That makes it sound kind of tractable, actually.
Yeah, yeah. I mean, I think at the institute now they're working on things like 3D codes and 3D inversion to actually work with the data. But I guess my feeling is always that stuff just new projects come up so fast, and it's such a data gathering place basically that would work with things like UBC codes and inversion software that exists might really accelerate the pace of work that's being done here, because it's a very geological institution, and the group that I worked with was all about MATLAB and writing code and understanding inversion and understanding Maxwell's equations and that kind of thing. But many of the groups were just thinking, okay, what's going on in the seafloor? We just want to understand the seafloor structure. We're not geophysicists in the slightest, so the end product is real value versus the methodological development there. And I totally see getting into the inversion level, its full 3D inversion level would just be a complete step change for them.
If you're going to prioritize the projects that you've seen in terms of sort of impact, or like, okay, that to do that would really be a step forward, both in understanding geologically or just from an instrumentation viewpoint. Like, which ones would you choose? There's the mud volcano.
I think the instrumental design is improved and improved. So I think I would go with the most recent, even though the mud volcano somehow it's like the one that I started with, and I think all of us would kind of want to see something come out of that. But the data quality is massively improved, and just the acquisition at sea and just the protocols that they were using and the way that they were actually laying out grids. Like, you can kind of see the evolution of this sort of random survey grid on this mud volcano to having straight lines, to actually just like going along a ridge versus perpendicular to a ridge and all that kind of thing. I think they were in the Black Sea. They were offshore Italy. They were over the Mid-Atlantic Ridge. So I mean, every time I call them, they're somewhere else. So my expectation, or I imagine that there is so much more, and every time it becomes better quality. So I'd love to see the mud volcano worked on, but I'll bet you that would be the toughest one.
So
data quality wise,
it's a time domain system.
it's a time domain system. So
but like you mentioned yesterday, with like the
synchronization
issue,
yeah,
they sort of overcome.
They were able to overcome that.
Nice.
All the receivers have very high precision clocks on them.
Do you know where's their base frequency?
It was 8 seconds, I think. I think, but don't quote me on that, because I think it was changed for all the different surveys.
Oh, nice.
Yeah. It's back forward. Yeah.
Joe. I don't have anything to present up there. Just kind of talk about what the interests are. So the research has been does work monitoring time-lapse gravity data for converting to reservoir properties, time-lapse gravity data. You can get permeability processes. You can do location. So also bringing EM data, electrical data as well. Gravity data is good. Expectation values. Really nice relationship between the two. Even electrical EM, we need to deal with all the problems that mixing laws, to all the connectivity estimates, fluid changes, law, we want to use that to do it That's my next step there. Apply this process to real world applications. Other thing that I'm interested in, I do work in model building. It's still like a generally time consuming process to work about build a big 3D model with something. The tool that's going to be at some points, and they're usually really expensive. And if you want to test algorithms and inversion algorithms, you need to come up with
models that represent real world applications or work. So I've been using
Yahoo knows about it, right? I'm building models. Yeah, it's been 1 week.
Model on Minecraft.
What's fun is that there's a lot of modifications that different filers that you can take advantage of. Like Geologic Survey of Sweden, they mod for the mods for the game that adds up all these different types of sedimentary igneous metamorphic rock types to them, and also rules about how they can spawn inside the game world in the 3D environment. And it actually generates somewhat realistic topography and subsurface structure, and essentially endless. So you give it a random number or a random seed, and you instantly have this large 3D volume of unknown geology that you can throw data at, or throw physics at, and get information out of it. So it makes for really good testing. The world itself is in a very regular geometry, 1 meter cubes essentially, which is really, really small and fine. So you need an efficient way to translate the geometry of the world into measures that we can quickly operate on. So you could just take it 1 for 1 and do a forward operation on it, but it would be all the top parameters. Automated mesh building using
So if you've got something on a really small scale, upscaling is always a big issue, right? You know, so we're talking about upscaling in geology, but we also have upscaling on physical properties. So if you had some kind of a rule for upscaling, can you then employ that into Minecraft somehow and say, okay, so let's suppose I've got electrical conductivity, and maybe I'm going to do harmonic averaging or something like this. Can you actually incorporate that rule into Minecraft and have it do the upscaling and repopulate things?
Well, it's kind of a issue because you could travel around in the game world, so it would change where you are. Everything is still local to your player. And it's not just generated at one spot in the model and then out from there. It's generated at every spot in the world, essentially. If that makes sense. If you could be in one spot and the geology is really fine, and then you go to another spot, like miles and miles away, and the geology is still really fine in that area. So it's the rules are consistent within each area of the game. And it's more of an issue of translating the rules far away from you into larger areas and downsampling that area.
It's multiple people building that full geological model there. Is that I just a little lost.
So the geology is still changing. The geology far away from you is still changing at the same rate that the geology close to you is. It's not like it's changing slower the farther away you are. It's still the same rules. That makes more sense.
Why did the geology change?
Because it decided to. It's all a procedure. Yeah, it's like it doesn't change in time. It just changes bases and rules about how the geology happens. So sedimentary layers can form. Sedimentary rocks form in layers, and then there's metamorphic rocks usually below them that are kind of blob shaped, but they they crosscut, they use rocks crosscut, they have kimberlite pipes that randomly show up.
So whoever designed this actually used to geology.
Yeah, similar with geologic survey of Sweden. About geology.
Oh, I see. No, I was thinking about like just the Minecraft design. But
Well,
this
it also came out of Sweden, right?
Yeah.
Well, through the years, there's never been a lack of geologists who've been most out of their jobs. They work in other areas.
So do you have input into what the models are, or they're randomly seeded, or how does that work?
Yeah,
Like, can
so
you
the
sketch
whole
one out?
world starts with a random seed. So
Okay.
it's defined based off of the one number, that one random seed. You don't really, there's rules, you know the rules about how things can spawn. So it's kind of like knowing rules about geology, like cross-fitting relationships, superpositions, layers. And there's also areas of the world called biomes that are different. So there's like plains biomes that are really flat and covered in grass. There's mountainous biomes that have big mountains in them. And the rules of the modification also change depending on what biome you're in. So it's just kind of background information, this synthetic form of background information. Like, okay, I know I'm in this environment. That means I expect to see these type of rocks here. Information.
There transition between biomes.
Yes, technically, that's another biome. So a transition biome is a type of biome. So that means you expect to find a mixture of rocks.
I'm just curious how deep.
The world essentially ends at it's very flat. You could extend it deeper and modify the game to go deeper than it does. Right now, I think the whole world is switched to about 256 blocks.
I think we need a demo. Okay, this has been great. I think we should probably break and have a little bit of coffee. I'm not sure where we get.
Not with the elevator.